For this video, we're finding volumes of solids of revolution. So we have 4 problems here, and I'm going to revolve the same shape around 4 different lines. So the shape is bound by y equals the square root of x, y equals 0, and x equals 4. So for the first one, we're going to revolve it about the x-axis. So here's my shape here. And then what I usually do is I draw on my axis of revolution. This is what I'm revolving it about. And I will draw a radius or 2 depending on what the problem calls for. You always start on your axis of revolution and draw to the outer edge of the figure, which is right there. Now there's no open space. I only ran into one line, and that's the end of my figure, so I know that this is the disk method. There's one radius drawn. That means that I'm going to have one radius in my problem. Since it's revolving, I know that the cross section will be circular, so our area is pi r squared. So that's the area formula I will integrate. The pi comes outside. I have one radius that I'm going to square. And then I look at it. That radius is represented by this one little green radius and is perpendicular to the x-axis, so I know that this is going to be a dx. Since it's with respect to x, my limits of integration will be x values. So I'm integrating from x equals 0 to x equals 4. The radius itself is the length of this line here, which is the more positive minus the less positive line it's touching. The more positive line is the square root of x, minus the less positive is just y equals 0. So this integral expression evaluated would give you the volume of the solid generated by revolving this area about this line. If we actually looked at the same area and revolved it about something else, we would get a different answer. So the same shape, but this time we're going to be revolving it about the y-axis. So this is my axis of revolution, and then I'm going to draw my radius on. So I start on my axis of revolution and go to the outer edge of my figure, and you can see that I hit my figure along the way, which means there's some open space, so I'll draw a second radius in there. And the radii can be drawn anywhere from where your figure starts to where your figure stops. They're just representative. So I know that since my radii are perpendicular to the y-axis, this is going to be a dy problem. I also know that there are 2 radii, so it's going to be a washer method, and I'm going to find the volume of the bigger figure first, and then I'm going to subtract out what's going to look like a little funnel shape. So it's going to be like a cylinder if I integrated this radius from here to here, taking away the funnel. If you can imagine, that's revolved around. So I have my big R squared minus my little r squared, and it's a dy problem, which means that my limits of integration are going to be y values. I know it starts at y equals 0, and it's going to stop at the y value right here. Well, that y value happens when x equals 4. So I can look at my equation. My y is the square root of my x, and x is 4, so my y value is 2. So 0 to 2. Next, you look at your longer radius. For my longer radius, the right-hand side, and that's the more positive side, is touching x equals 4. The left-hand side is touching x equals 0. So my longer radius is the length from 0 to 4, which is 4 minus 0, or 4. The shorter radius, the right-hand side, is actually touching the function itself, but remember this is with respect to y, so I'm going to take my equation, y equals the square root of x, and I'm going to solve for x. So x equals y squared. It's the same exact equation, just with respect to a different variable. I want y's. So the right-hand side is my y squared. The left-hand side is 0. And this integral evaluated would give you the volume of that figure spun around the y-axis. If we're spinning it around the line x equals 4, that's a vertical line. Here's our shape. We know that's 4. So our axis of revolution is right there. So when I draw my radius, I start on the axis of revolution, go to the outer edge of my figure. I can see that there's no empty space. There's one radius, so this is a pi with one thing squared, one radius squared. My radius is perpendicular to the y-axis, so this is a dy problem, which means we're integrating from our y values 0 to 2. And I have one radius, so I look at the right-hand side and it's touching x equals 4. And the left-hand side is touching my function, but with respect to y, so minus y squared. A lot of people get these confused. This has 2 radii, this has 1, and there are different lengths. This has a radius of 4 and a radius of y squared. This radius, if you look at this whole distance, is 4, and this little distance right here to the function itself is your y squared, so we're looking at the leftover part. For the next problem, same shape, all the way out to x equals 4, but we are spinning it around the line x equals 6. So that is out here. That's our axis of revolution. So I'm going to start my first radius here, go to the outer edge of the figure, and you can see I hit a line along the way. There's some open space here, so I'll need a second radius. When you have 2 radii, it's pi, your big R squared, the long one, minus the little r squared. Your radii are perpendicular to the y-axis, so this is a dy. We're keeping the same limits of integration, 0 to 2. You always look at your longer radius first. The right-hand side is touching 6. The left-hand side is touching the curve, which we know is y squared, so 6 minus y squared. If you look at the little radius, the right-hand side is touching 6, and the left-hand side is touching 4. And that is a distance of 2 from 4 to 6. 6 minus 4 is 2. So this integral evaluated would give you the volume for that solid described.